Hi guys. So, miss you tons. Today's video is going to be a little bit disjointed at times because this is all I have in my house for a whiteboard. And you know at school we take up both sides and right across the smart board and everything else. So just be patient with the weird little blends from one scene to the next. But the first thing I wanted to go over with you guys is amplitude. So if we had a flat string and we started wiggling it up and down, then we would have however far from where that flat string started to its maximum point away would be our amplitude. And that could be measured from the rest position to the crest, or it could be measured from the rest position to the trough, and it should be exactly the same regardless. So amplitude is maximum displacement from the rest position for a particle, and the unit for that is meters. Then wavelength is also measured in meters, and it is the distance between any two identical successive points on a wave, which probably kind of sounds like garbly gook. It just means that we can measure it between crest to crest or trough to trough, which is the easiest and most common thing that we do. But we could do something else weird. We could say from this point here where it starts to cross our rest position back to this point here where it starts to cross the rest position. That could be a wavelength. I could arbitrarily pick here on the downslope and the matching point here on the downslope. That would still be a wavelength. It doesn't matter. It's just that for ease, we typically go crest to crest or trough to trough. Okay, and both of those, the units are meters. So nice, happy, easy units. If you have any questions on that part, just let me know, and I will be looking in the comments after I post this. But we're going to go on to the next thing now, so hold tight. Okay, so now we have two different scenarios. We have a wave that's going through the exact same string. We'll just make it a string. So it's the same medium, which means that the velocity of the wave is the same for both scenarios. You can't change the velocity of the wave in a given medium. The velocity of a wave in a guitar string is the velocity of the wave in that guitar string no matter what you do to it. The velocity of sound in air is the velocity of sound in air, unless we change the humidity or the temperature of the air. Okay, velocity of sound in water is the velocity of sound in water, again, unless we mess with the temperature or add salt to it or do something odd like that. So it's going to be constant because we're going to just use a regular old string for this one. So it's going to be the same for both. Okay, so for this one, this is a low frequency wave. Frequency, or how many cycles per second our little nervous science guy would see coming at him. Okay, so if we look at it, how many wavelengths are in this string? Well, we have 1, 2, we have 3 wavelengths. Okay, so 3 wavelengths. Okay, and on this one down here we have how many wavelengths? We have 1, that's 1, 2, 3, 4, 5, 6, and 7. So for this one we have 7 wavelengths that are coming at him. Okay, so this one he's seeing many more waves come at him, which means that his frequency has to be higher. Okay, more wavelengths, higher frequency. More waves, higher frequency. Okay, and it's kind of like, this is like your little brother or sister just kind of tapping you, like annoying you while you're trying to do your work. And this is when they come up behind you and they're like, I need your attention. Please pay attention to me. Pay attention to me. I gotta talk to you right now. And they're just tapping you like crazy. So higher frequency is the more annoying, lower frequency is less annoying. Okay, so he's seeing less wavelengths, higher frequency, or sorry, lower frequency. Less wavelengths, lower frequency. He's seeing more wavelengths, so higher frequency. Okay, but what about the actual wavelength itself? If we looked at the wavelength itself, how long is the wavelength here compared to here? Well, if this is a wavelength and this is a wavelength, I think we can agree this one is about half of the wavelength up here, right? So shorter wavelength, if there's a higher frequency, longer wavelength if there's a lower frequency. Okay, higher frequency, lower wavelength. Okay, yeah, there's more waves, there's more wavelengths packed into there, but that's because they're itty bitty. It's like packing in a whole bunch of little gumballs here versus trying to pack in basketballs up here. Totally different, right? Different sizes, so you can pack more gumballs in the same space than you can pack basketballs in. So you can kind of look at it as that way. If we've got lower frequency, the wavelengths can be longer. If we have a higher frequency, the wavelengths have to be shorter, because it just won't fit otherwise. Okay? So now we're going to move on to the wave equation and how to do the calculations with that. Hold tight. Okay, so before we move on to the wave equation, I want to go over the difference between frequency and period. Frequency is the cycles per second, like we talked about. However many little crests that guy sees coming at him, that tells us how frequently he's seeing a wave come towards him. So that's how many cycles per second. The unit for that is hertz. Okay? Then we have period. Period is how many seconds it takes for him to see one cycle come towards him. Okay? And that tells us the reverse of frequency, or the inverse of frequency, I should say. So frequency is 1 over the period, and we can say it the other way around. Period is 1 over the frequency. Okay, and most of the time we're dealing with frequency. Okay, but occasionally it's useful to know what the period is. So just so you understand the connection between those two. How many seconds for a cycle versus how many cycles in a second. Okay, so now we're going to move on to the wave equation. This is the one I've been telling you guys all year long. You'd love this unit because it's so simple on math. So our wave equation is velocity is equal to frequency times wavelength. This funny looking thing that kind of looks like an upside down, slightly squished Y is lambda. Again, ran out of letters, I don't know. Okay, so lambda stands for wavelength. So we've got velocity, which is the velocity of the wave, or how many meters that given point on the wave, like your crest or your trough, moves in 1 second. The unit is meters per second, just like all the velocities that we've dealt with this year. Frequency, just like we just talked about, how many of those points that guy's seeing come at him, okay? And then the unit there is hertz, which is the same as 1 over a second. And lambda, our wavelength, the unit is meters. Okay, so if we look at this, our units here are meters per second. We have frequency, which is 1 over seconds, times our wavelength, which is meters. Ooh, my handwriting's getting worse without being there with you guys. Okay, so we have meters over seconds. Does that equal out meters over seconds? Yeah, we're good. Okay, so now we're going to go on to some practice. One plus is this board's a lot faster to erase. Okay, So, you guys are going to have a worksheet called Waves on a String, and we're working with a string who has a known velocity of 600 meters per second. That's the fast speed that the waves can travel through it. Okay, so we have for number 1, if a wave with a frequency of 262 hertz, we want to know what its period is. So we're going to do our knowns and unknowns chart, just like before. Knowns, unknowns. Okay, so we have frequency. Oh, we also know our velocity. That's going to be the same for all of the problems on this worksheet because they're all to deal with the exact same string. Okay, and you're asked to find the period of the wave. So we need to know what its period is. And you're also asked to find its wavelength. Okay, so we have a couple of equations. We have our wave equation, but we also had the equation that was on the last clip, which was T equals 1 over F. So period equals 1 over frequency. So we need period. We have frequency, so we can do that. Okay, so we take 1 divided by 262, which I should probably grab my calculator because I'm not going to do that one in my head. Okay, and I'm going to get 0.0038, and it goes on and on and on. It's fine. You can just round it to a couple of digits out there, and we'll put it in scientific notation. So 3.8 times 10 to the negative 3. But what are my units? We have hertz on the bottom. Inverse hertz? Well, we said hertz is the same thing as 1 over seconds, right? So if we look at this, to get rid of the seconds down here, we'd multiply by seconds. And whatever we do to the bottom, we do to the top. Those die, and we're left with seconds. Okay? So now we have the period. But we're also asked for the wavelength. Sorry, having to erase every time. Okay, so for wavelength, we're given frequency and velocity. And we know this now, so we could put this over here, that we now know it was 3.8 times 10 to the negative 3 seconds. Okay, but if we need wavelength and we're given velocity and frequency, we can rearrange this one. Okay, so to get wavelength by itself, I'm going to divide both sides by frequency. And those are going to die and die. And we wind up with wavelength equals velocity over frequency. Now we can plug in 600 meters per second over 262 hertz. Okay, and then just to make the units easier and happier, I'm going to wipe out hertz and I'm going to change it to 1 over seconds. Okay, so now we can see our seconds are going to die, and we're left with meters. So at least our units are happy. And we can take our velocity of 600 meters per second divided by the 262 hertz, and we get a wavelength of 2.29. Again, we're just going to round off to a couple of digits past the decimal. I'm not going to worry about sig figs. And our units are meters. Okay? Okay, I'm going to suggest you pause the video right there and try number 2, and then come on back to it and see if you worked it out properly. I'm going to go ahead and start number 2. We're going to have our knowns and our unknowns. Okay, and our first known is at the top of the page, and that's our velocity, 600 meters per second. Okay, and our second known is our frequency, 294 hertz. And again, I'm looking for the period and the wavelength. Okay. So for period, I'm going to come back up to this equation. Period equals 1 over frequency. So 1 over 294 hertz, and I'm going to rewrite that immediately as 1 over seconds. So if we take 1 divided by 294, and again just round it off to a reasonable place, 0.034. This seconds, to get rid of it on the bottom, we multiply by seconds, they die, and we have our units of seconds. Okay, or if you have it in scientific notation, 3.4 times 10 to the negative 3 seconds. Okay, then we're going to move on to solving for wavelengths. Okay, and if we're looking for wavelength, we're going to use our wave equation. So velocity equals frequency times wavelength. Solve it for wavelength, and we rearrange and get wavelength equals velocity over frequency, right? Divide both sides by the frequency. So 600 meters per second over 294 hertz. And hertz I'm going to write as 1 over seconds. My seconds die and die. I'm left with units of meters, and I have 600 divided by 294. I have a wavelength of 2.04 meters. Okay? The rest of those, I will post the answers on Google Classroom on your worksheet for the rest of that one. We're going to practice these for a couple of days, and then on Friday we will get together and you'll have a chance to ask any questions that you have regarding how to work these problems through. So do the best you can, guys. I miss you like crazy. Take care of yourselves, stay healthy, do everything you're supposed to do, and I hope to see you this coming fall. Bye.